We are continuing with angular momentum. In the previous two modules, I talked about the definition of angular momentum, what is the angular momentum operator, what is L square and Lz, Lx and Ly, and then I talked about the eigenvalue corresponding to angular momentum. Then I also talked about what is the physical interpretation of the eigenvalues obtained from the angular momentum. Okay, so in this particular module, there is a concept of angular commutators, which is very important in angular momentum, and that we will decide. Okay, commutators, if you remember, I talked about in details when I was talking about the operator algebra, and I said you that if you have two operators A and B, which when operated on a function f, okay, and if you operate it in this fashion, B, A, and then f, then operators are operated in sequential manner from right to left. So in this case, B will operate first on f and it will give you a function this way, and in this case A will operate first and it will give you another function f double prime. Okay, so this sequential operation, if you do by two operators A, B, and if you calculate the value of the whatever you obtain, and you calculate the value of AB minus BA, then whatever value you get is the value of the commutator. This is normally written as A, B within bracket, and this is called commutator. Okay, so with respect to angular momentum, these commutator relationships are very important. So in this module, we will be talking about the relationships of commutators with respect to Lx Ly, Ly Lz, and Lz Lx. These are the values. If Lx Ly is equal to I h cross Lz, Ly Lz is I h cross Lx, and Lz Lx is I h cross Ly. When this value is equal to 0, we say A operator and B operator commute with each other. Commute with each other. If the commutator AB is not equal to 0, then we say A and B do not commute. So what do you get? Lx Ly do not commute, Ly Lz do not commute, and Lz Lx do not commute. Okay, and we say the precise it was written there. The precise value of the three components of the angular momentum cannot be measured simultaneously. The significance of this commutator relationship is that any two operators, if they do not commute with each other, then they cannot be determined precisely and simultaneously, and the variables corresponding to these operators are called conjugate variables. Okay, so Lx and Ly is non-conjugate variables, Ly and Lz are non-conjugate variables, and Lz, Lx are non-conjugate variables. So they cannot be determined simultaneously and precisely. Okay, the precise value of the three components of the angular momentum cannot be measured simultaneously. Okay, so this is the significance of this commutator relationship. That whenever you have to see that whether A, B is equal to 0 or not, whether they are commuting with each other or not. If it is 0, then only you can determine the precise value simultaneously and precisely. Otherwise, you cannot determine. Okay. If you look at this, the other commutator relationship, L square Lx, L square Ly, L square Lz, what you find that all this commutator relationship is equal to 0. I will give you one example also. We will try to find out this relationship, but final relationship is this one. So what you see is the total orbital angular square of the total orbital angular momentum, and one of the component is commuting with each other. Means if you want to find out orbital angular momentum, then you can find out the total orbital angular momentum and one of its component, either Lx or Ly or Lz, which is normally what in quantum mechanics we talk about Lz. So L square and one of the component Lx, Ly or Lz commute, and hence simultaneous determination of L square and Lz is possible. L square Lx is also possible, L square Ly is also possible, but normally we treat Lz as component is taken as the main component, and this we talked about, and this value, so because LZ, if you operated on, you have seen just in the previous module that when you operate LZ on phi value, phi eigenfunctions, then what you get is MH cross phi wave functions. So LZ operator, when operated on phi functions, gives you an eigenvalue called MH cross. Okay, that's magnetic quantum number into H cross raised divided by 2 pi. Okay, so that's why LZ is important. Lx and Ly we did not operate in the previous module also. We operated with Lz and we operated with L square on the theta function, and we got L into L plus 1 H cross plus theta function in case of L square. So these two values, L square and Lz, can be determined precisely and simultaneously, and we will talk about the component Lz and component L square, and that's why this relationship is important. L square Lz commutator is 0, and these relationships are important because simultaneous evaluation of all the components Lx, Ly and Z is also not possible. Okay. Now, if you want to check it whether these relationships exist or not, this is the final relationship. So let's do one of the commutator relationship, that is Lx, Ly. So Lx, Ly will be Lx, Ly minus Ly, Lx, as AB minus BI I have written just now. And this is the commutator, Lx is equal to H cross by I, Y del by del Z minus Z del by del Y. These relationships, if you want to see, you go and see in the previous module. These modules are to be seen in the sequential manner, then the concept will be better. Okay, so whenever you are reading the angular momentum, then start with first module and then go for the second, third and fourth, and always you must have a pen and paper with you. You do it yourself, then only you will learn quantum mechanics. Okay, so what is it happens? If you write Lx multiply this multiplied by this will give you this one, these two will give you this one, and similar multiplication will give you four different terms. Y del by del Z, this is H cross by I, this is H cross by I, so it will be H cross S square minus H cross S square. Okay, because it will be I square, so it will be minus H cross S square. Now you have Y del by del Z, Z del by del X minus Y del by del Z, X del by del Z minus Z del by del Y, Z del by del X, Z del by del Y into X del by del Z. Now the only thing is that you have a differential. If you concentrate on this one, you are differentiating by Z with to the two terms Z and del by del X. Okay, so you will keep one of the term constant and you will differentiate the other one. Then in the next plus you keep the first term, second term constant and differentiate the other one. Okay, and if you do that, and if you use this, that when you differentiate x with respect to z or y with respect to z, it becomes equal to 0, obviously, and del z by del z will obviously become equal to 1. If you use these, then the relationship which you get is from the first term you get these two terms, y del by del x, y z del square by del z del x square. Then from the other terms you get these values, yx del square by del z square, z square del square by del y del x, zx del square by del y. That you can do. You have done on differentiation. So first and second term. So you get Lx Ly value we obtained. Similarly, Ly Lx value can be calculated. So the only thing is that the direction of the application of operator will change, and so the Ly Lx will become H cross by I, Z del by del X, X del by del Z. So it is Ly. You see, Ly will start, if you write Ly, then it will be this one, and if you write Lx, it will be this one, Y del by del Z, Z del by del Y. So again the same thing, you multiply these and you will get 4 different equations, and after this 4 different terms in the equation, and after this what do you get? Finally you get this equation, Ly Lx is equal to this one. So you have with you Lx Ly also and Ly Lx also, then subtract these two, and subtracting gives you this one. If you subtract this, you look at the equations, every term will go except these 2 terms. This term will remain there and this term will remain there. Rest all term will go. Okay, you see minus z square del square by del y del x square, minus z square del square by del x del y, and you have a negative sign here, so it will become positive and it will go. So similarly all terms will go, and what you will get is Lx Ly minus Ly Lx is equal to minus h cross square y del by del x minus x del by del y. Okay. Then what I have done, I rearrange this one, x I brought this side, y I brought this side, and you get h cross by I h cross. So I and I will go, you will have h cross, okay, minus h cross, this one, and then you have h cross by I, okay, h cross by I we can write, minus sign is I square, so one of the I will be there here, and you can write this one, so it comes out to be I h cross Lz, okay. So this equation from this is your commutator Lx Ly we proved. Same way you can go and prove Ly Lz and Lz Lx. Ly Lz you can find out, Ly Lz you can find out, operators, these are operators, so a symbol for operator should be there, and this you can practice and see the first relationship which I have given you, you get it or not. So the final equation, the one thing which we got is that the component of the angular momentums do not commute with each other. Lx Ly, Ly Lz and Lz Lx will not commute with each other. Then the next relationship which I said you, that if you have the total angular momentum and one of the component will commute with each other. So let us try to find out commutator for that also, and for this in this commutator relationship, in this derivation, I have used all the relationships of the Lx Ly in the Cartesian coordinate. In the next, I will be using the spherical polar coordinates, where Lz is minus I h cross del by del phi, and L square is minus h cross square 1 by sin theta del by del theta sin theta del by del theta 1 plus 1 by sin square theta del square by del phi square. Okay, this you don't need to remember because you already know the conversion of Laplacian operator. Okay, so somewhere I'm wrong. Conversion of Laplace, I will omit it. First, let me write it in this way. Del square psi was what? It was 1 by r square del by del r square del psi by del r plus 1 by r square sin theta del by del theta into sin theta showing time lag. This pen is not working. There's something happened with this one. Okay. Del by del theta sin theta, sorry, del by del theta, del by del theta, okay. So you see the first part you omitted, then you see r square you omitted, and rest of the term is same, 1 by sin theta del by del theta sin theta del by del theta is the first term. Then in the last term which you have is 1 by r square sin square theta del square by del phi square. So omit this r square, and you see rest of the term is same, 1 by sin square theta del square by del phi square. Okay. So only one relationship which you have to remember is that how to convert Laplacian operator in Cartesian coordinate to Laplacian operator in spherical polar coordinates. If you remember that one, then you can write the relationship for L square very easily. Okay. So if you have both the operators, then what you will try? You will try to operate with these operators in sequential manner on a function. Okay, say any function we can write. Okay, I omitted it because this thing we did earlier. Now you see, what is this? L square Lz multiplied on a function f. So write the L square equation minus h cross square 1 by sin theta del by del theta sin theta del by del theta plus 1 by sin square theta del square by del phi square, and then write the operator Lz, which is minus I h cross del by del phi into f. Okay, and what does it mean? It means that the function is f, just a symbol f I have taken. So we can write it like this one. I did nothing but minus I h cross and minus h square I multiplied, then minus minus plus I will remain there, h cross whole cube, and this f came inside the bracket del f by del phi I have written. Okay. Now what you can do, you can again bring this all these red terms within the bracket, and it will be like this one. So L square Lz f will be is equal to minus is equal to I h cross cube 1 by sin theta del by del theta sin theta del square f by del theta del phi. You see here, it's del theta del phi, and then you have 1 by sin square theta del cube f divided by del phi square. This was del phi square and del phi, so it's del phi cube. Okay. Now once you have this one in the, L square Lz, then you can calculate Lz L square, and if you calculate Lz L square, what do you find? It's now the position of the two operators is changed. You will operate first with the operator of L square and then with the operator of Lz. That's right to left. That is always followed. Okay. So what do you get? This f comes inside, I h cross whole cube will be there, and now then multiply with this one, the function we have written. So the multiplication will give you the same equation. Okay. And this del square f del theta del phi and del phi del theta is the same thing. So if you compare this with the previous equation of L square Lz, it is the same equation, and if it is the same equation, then you can write L square Lz f and Lz L square f is same thing. So you get a equal to 0, this commutator equal to 0, and this was the result which on the very first page, that total angular momentum and one of the component of the angular momentum commute with each other. So simultaneous determination of total orbital angular momentum and Lz component of the angular momentum is feasible, is possible. Okay. Now one of the characteristic of this commutator, this commuting operators, is that they have common set of eigenfunctions. They have common sets of eigenfunctions. This is also very important to understand, that when the two operators are commuting, then both these commuting operators will have a common set of eigenfunctions. So let us see what does it means. Operators that commute have a common set of eigenfunctions. Now I am writing two operators. One is operator A, which when operated on phi A gives you an eigenvalue small a and phi A. Then I am writing another operator B, which when operated on phi B gives you an eigenvalue B along with an eigenfunction phi B. Okay. So both these are eigenvalue equation for two operators A and B. If you have to find out and then you suppose that A and B commute with each other, and if A and B commute with each other means AB minus BA when operated on phi A should give you 0. That is what is the commutator relationship means. So what does it mean? If you write this relationship and you operate it in a sequential manner, then what does it give? AB phi A minus B, and the first operation will be with the A on phi A. And if you operate with A on phi A, this A phi A is already a small a into phi A. So a small a phi A from the eigenvalue, first eigenvalue equations, you can write this one. And so it's very simple. We can write this as, now this is a constant eigenvalue, so bring it this side and write B phi A. Now you see, it's here you have B phi A and here also you have B phi A. Okay. So A into B phi A is small a into B phi A. It means when you operate with an operator on B phi A, you get an eigenvalue A along with the eigenfunction B phi A back. Okay. So phi A is an eigenfunction of A with eigenvalue A. Phi B is an eigenfunction of B with an eigenvalue B. B phi A is also an eigenfunction of A. This relationship tells you that B phi A is also an eigenfunction of A. Okay. B we did not operate on phi A. We operated on A phi A. So B phi A is also an eigenfunction of operator A with eigenvalue A. So instead of A, we write B phi A. When B is operated on phi A, it gives you value C, because you don't have B operated on phi B gives you B, but B operated on phi A gives you another constant C into phi A. So phi A is an eigenfunction of B also. Okay, and phi A is an eigenfunction of A also. So A and B both commute. If A and B both commute, then phi A is the operator of A also, and phi A is eigenfunction of A also, and phi A is eigenfunction of B also. So both these eigenfunctions are the eigenfunctions for operator A and B. This comes from the fact that AB minus BA into phi A is equal to 0. Only when you get this commutator relationship, then only you can get this equation. Okay. So this is very important. What we proved is that phi A is an eigenfunction of both A and B. Phi A is an eigenfunction of both A and B. Okay. Hence, and if it is so, then A and B is commuting. So any property corresponding to A and B, A or B operator which is representing some physical variables, can be determined precisely and simultaneously. I said you that this is what is the purpose of doing commutator relationship, that you can determine which of the properties could be determined simultaneously and precisely, and which properties cannot be determined simultaneously and precisely. So what we did is that since L square and Lz operator commute with each other, so you can have the value of total angular momentum and one of the component of the angular momentum, and if you have the relationship Lx Ly is not equal to 0, Ly Lz is not equal to 0, and Lz Lx is not equal to 0, then these components Lx, Ly, Lz cannot be determined simultaneously and precisely. That is why commutator relationship is very important in angular momentum. It's important at other places also, but in case of angular momentum, the only two properties of the angular momentum which you can determine is the total orbital angular momentum and Lz component of the angular momentum simultaneously and precisely. Okay. Now from this, what we can do is that magnetic quantum number value is limited by azimuthal quantum number, that you know already, that if L is equal to 2, M has values +2, +1, 0, -1, -2. Then you say the total number of values which is possible is 2L plus 1. 2L plus 1 is the total number of values possible for magnetic quantum number. So if L is equal to 2, you will have 5 values. If L is equal to 1, you will have 3 values. That you know, +1, 0, -1, and then your box diagram, all this we have done. Look at from the angle of this operator algebra and magnetic quantum number. Operator algebra and the operating with the Lz and L square operator. What do you get? This you have done already, that when you operate with Lz on a function, this is any function, I will not say what function it is, it's any function, then what do you get? You get an eigenvalue mh cross. This we did earlier also, and this we did when I was talking about rigid rotor also, that when we got the function 1 by root 2 exponential plus minus im phi, there also I said you what is the significance of these functions, and then physical significance of the functions. Then I talked about Lz operation on the functions. Okay, so this equation is known to you. Then when you operate Lz square, what will it give you? Lz square means operating with Lz twice. So Lz square ylm cos theta will be Lz, and again if you use this one Lz ylm, so you could have written Lz ylm cos theta, and instead of Lz ylm cos theta I have written mh cross ylm cos theta, that I can write, because this represents the first operation by Lz will give you this one, and then the second operation remains here. So if you again operate it, it will give you m square h cross f square ylm cos theta. This is the value of operation of Lz square. If you again, this equation is known to you, that when orbital angular momentum operated on a function, it is equal to h cross s square L into L plus 1 ylm cos theta. Ylm cos theta is a function, okay, or spherical harmonics I am saying. Okay, so this is the value which you get. Now what we do is that we subtract these two equations. From this L square equation, you subtract this one. I write equation 1, sorry, I write equation 1, equation 2, equation 3, and subtract 3 minus 2. 3 minus 2. So it will be L square ylm cos theta on the left hand side minus Lz square ylm cos theta. Okay, and then on the right hand side you will have h cross s square L into L plus 1 ylm cos theta minus m square h cross s square ylm cos theta. Very obvious. Then what you can do is that ylm cos theta is common, so this will be L square minus Lz square, and this will be h cross s square L into L plus 1 minus m square h cross s square ylm cos theta. And this L square minus Lz square, if you remember, what was L square operator? L square operator was, in the definition I talked about, Lx square plus Ly square plus Lz square. So L square minus Lz square you can write as Lx square plus Ly square. So you replace this L square minus Lz square by Lx square plus Ly square. Okay, ylm cos theta will remain there, and the rest of the thing is same. Okay, you can bring h cross s square also outside, but anyway it doesn't matter. So you have Lx square plus Ly square. Now this is sum of the two components, which is Lx and Ly, a square of the two components, sum of the square of the two components. So this has to be always a positive number. Okay, so this also has to be a positive number. This part also has to be a positive number. And for being positive, this value h cross square L into L plus 1 must be greater than m square h cross square. So eigenvalue of Lx square and Ly square has to be positive, and hence L into L plus 1 minus m cross square must be greater than 0. So h cross square L into L plus 1 greater than or equal to m square h cross square. So I said it's the sum of the square of the two numbers, so it will be a positive number. So this also should be a positive number. This also should be a positive number. And if this has to be positive number, then you can write h cross square L into L plus 1 is greater than or equal to m square h cross square. Or if you remove h cross square, then you can write L into L plus 1 must be greater than or equal to m square number. This is how the azimuthal quantum number limits the value of magnetic quantum number. Okay, but because magnetic quantum number value will always be decided by L into L plus 1. It has to be always less than L into L plus 1. Okay. So the magnetic quantum number value is limited by azimuthal quantum number. Once we have this basic understanding of these things, then another important concept in angular momenta is the concept of ladder operators. And this we will cover in the next module. Okay, thank you.